Oh, hello. Thanks for the opportunity to speak. I'm Sindhu, a PhD student at TIFR Mumbai. The theme of my talk would be supermassive black holes in the first billion years, slightly different from what we've been talking since morning. So these are supermassive black holes at redshifts about 6. So data is sparse over there. Fine. At redshifts of 6, data is sparse, but that's going to change soon because of the multiple surveys that are coming up, like LSST, Roman, Euclid, that we'll be talking about. But my objective here is to motivate search for obscured quasars at a high redshifts. And I'll be talking about why there's a need for obscured growth of supermassive black holes in the first billion years. Right, so accreting supermassive black holes are visible to us as quasars. More than 200 quasars have been detected at redshifts about 6. And the interesting part is that most of these supermassive black holes are already as massive as 10 to the power 9 solar mass when the universe was less than just a giga-year-old. Now, we don't fully understand how these black holes have grown so quickly, so huge, so early on in the universe. Well, black hole accretion process is a complicated process that spans across several scales from parsecs to kiloparsecs. So doing a full simulation is certainly difficult. Here we instead consider a simple heuristic model wherein the accretion rate of the supermassive black hole is proportional to the mass, so that you have the black hole mass growing exponentially with time, as shown in the red curves in this plot here. So if you know what the seed mass of the black hole is and the seed redshift of the black hole is, and if you know what the lifetime of the quasar, that's the time for which the supermassive black hole is active, then you can just use the exponential to compute what the black hole mass should be at a given redshift. Conversely, since we already know the black hole masses, we have observed black hole masses, if you're able to measure either of one of these parameters, you'll be able to constrain the other. But usually these seed black holes are at very high redshifts and difficult to observe. What we can measure are quasar lifetimes, as I will show in a little while. So if quasar lifetime is known, one can then back calculate, given the black hole mass, what the seed should be. And so it's important, and knowing the seed masses, each of these seed masses can lead to a different growth mechanism. And so you can constrain the supermassive black hole growth. What I'll now discuss is a method to measure quasar lifetimes called the proximity zones. So in the bottom here, you're looking at the rest frame UV spectrum of a redshift 6 quasar as seen by an observer today. Basically, while the UV light from quasar travels to us, two things happen. First is, because the universe is expanding, UV light is redshifting to optical. Secondly, the UV light can get absorbed and scattered away from our line of sight due to the presence of intergalactic neutral hydrogen clouds. So at redshifts of 6 or above, since the universe was mostly neutral, most of the light gets scattered away and you see almost no absorption, except in this particular region called the proximity zone, where there is still non-zero transmission left blueward of the Lyman alpha emission line. Now this corresponds to the region around the quasar in the IGM that has been ionized because of the presence of the quasar. So essentially, proximity zone sizes are a proxy to the ionized bubbles around the quasar. So more ionization, less neutral hydrogen, and so you see more transmission. And so for two different quasars in similar environment, you would expect that younger quasars have a smaller bubble size or a smaller proximity zone sizes, because they wouldn't have enough time to ionize enough hydrogen. So essentially, proximity zone sizes are a probe of quasar lifetimes. One can then construct models where you study the evolution of proximity zone size as a function of lifetime for different quasar parameters, such as its magnitude and redshift, using cosmological simulations, and then simulate Mach spectra like this and compute the proximity zone size from Mach spectra. So from observations, using this one single number called the proximity zone size, RP, you can then estimate what the lifetime of that quasar should be. Eilers et al. In 2017 were the first to use this method to estimate quasar lifetimes. And what they found is, interestingly, a certain population of quasars that had lifetimes of less than 10,000 years. Now, this is a problem for the black hole seed models, because if you had only 10,000 years to grow a black hole, then the required seed masses fall outside the range of known black hole seed models. And so, yeah, this is basically the crisis of supermassive black hole growth, where proximity zone-based quasar lifetimes are too small to explain black hole growth from known black hole seeds. In our work, we try to resolve this growth crisis by looking at certain assumptions that are made in theoretical modeling of the proximity zone sizes. Basically, previous works have assumed they have made simplifying assumptions about the effect of quasar environment and the effect of quasar variability on the proximity zone sizes. So to answer the first question of what the quasar environment looks like, we've used the most successful reionization simulations that are able to reproduce a lot of observations, including the latest Lyman alpha optical depth measurements. And so in our simulations, inhomogeneous reionization with large residual neutral islands out to redshift 5.5. Reionization ends at as late as 5.3 in our simulations. And we also have a large dynamic range of halo masses. So I take these simulations, populate halos with quasars, and then use a line of sight radiative transfer code that I've written to compute Mach spectra. And from the Mach spectra, I can then study the evolution of proximity zone size as a function of lifetime. Now, this is showing RP versus TQ for 3 different scenarios where the environment around quasar is completely uniformly ionized or patchily ionized, given by our models in green, or uniformly neutral. And so the solid curves are the median, and scatter shows the scatter between sightlines from a simulation. And what one can notice is that from our models, we have a lower proximity zone size distribution compared to a uniformly ionized case, and the difference is larger at higher redshifts. But the bottom line is that for a given proximity zone size now, our models will predict a longer lifetime with a larger spread. We then look at the distribution of all known proximity zone sizes and see what the lifetimes could be, and by comparing them with distributions from our simulations. So as you can see here, most of the measurements are consistent with a 1 megayear or 100 megayear lifetime, but then there are still certain outliers that require a lifetime of less than 10,000 years again. Although this fraction is now smaller after incorporating the patchy IGM as compared to the uniform IGM models. So patchy reionization can mitigate this crisis, but cannot fully resolve it. We then look at the effect of quasar variability. As some of you might have already guessed, quasars are very much variable. Massive black holes can be active and inactive, such as the one in our own galaxy. And so we try to parameterize the quasar light curves using a simple toy model where the quasar turns on and off periodically. And such a model can then be parameterized by just 2 parameters, the duty cycle and the on time. And the on time is just basically the duration of each of these episodes. And duty cycle is the fraction of total time that the quasar is active. And now we study the proximity zone size distributions in such a model for different values of duty cycles and on times. So essentially, all the models that we had so far were duty cycle 1, which assumed that once the quasar is on, it's always on. We then again look at the distribution of proximity zone sizes and find that short duty cycles with short periods with short on times can cover these small proximity zones that required very small lifetimes earlier. More importantly, what we found was that keeping the duty cycle short and increasing the on time, we are able to find a model which can explain all the observed proximity zones for lifetimes as large as 50 megayears for the first time. And we then supplemented this with more measurements from the XQR30 survey using the VLT telescope. These are our recent measurements. I'll probably have to rush here. So, and then our measurements are also in the same redshift range as from 5.8 to 6.5, and we found that they're consistent with previous observations. And they've strengthened our case for variable quasars when compared to the distributions from our simulations. But coming back to the question, is this variability consistent with the black hole masses? So I have now information about the duty cycles by comparing proximity zone sizes from observations and simulations. And then I have the black hole masses independently. The way I connect these two is through the exponential model. And now for the duty cycles that we inferred from observations, we still find that even with a duty cycle of 30%, a redshift 15,000 solar mass seed would require 2 gigayears to grow to 10 to the power 9 solar mass, which is much larger than the age of the universe at this time. We then tried to work around this problem by introducing what's called the accretion duty cycle. So this accretion duty cycle is now a sum of the luminosity duty cycle, which is basically the duration for which the supermassive black hole is accreting and is visible to us as a quasar. Basically, the F duty that I'm determining here would be the F duty luminosity, plus an F obscuration, which is basically we're allowing for the black hole to accrete while it's not visible to us. And there could be obscuration because of dust or because of orientation effects. And with such a model, one can then compute that accretion duty cycle of 0.7. And with a seed mass of 10 to the power 3 at 15 redshift, one can grow a 10 to the power 9 solar mass black hole by redshift 6. So of course, this obscuration parameter has degeneracies with this black hole seed masses, as you might have already noticed. And so this plot here shows how the obscuration fractions change with the assumed model for seed masses. But if one is able to measure the obscuration fraction, then one can break this degeneracy and put constraints on black hole seeds and therefore the black hole growth. And we've tried to do that by proposing a search for observing a redshift 6 quasars using WST. And yeah, this is something that could also be done using LSST. If you're in common terminology, these are type 2 AGN. And so this is basically the summary or moral of the story. So supermassive black holes were hard to reconcile with quasar lifetimes derived using proximity zones. We have factored patchy reionization and quasar variability into this proximity zone modeling. And then we found that patchy reionization can mitigate this crisis, but not fully. But short duty cycles and short episodic lifetimes are consistent with the observed distribution, but then they're still hard to reconcile with the observed black hole mass unless there is UV obscured growth. And search for such obscured quasars will be potentially able to constrain supermassive black hole growth parameters. Thank you.
We have time for a couple of questions.
Yeah, so thanks for the interesting talk. So even with all of this combined, it seems like you still end up with a seed mass of, say, 10 to the 3 to explain current observations. So what does that mean about the formation channels for these? Does that mean that it's basically impossible, even when you account for all these, to have, for instance, population 3 remnants causing these?
Yes, yes. So a 10 to the power 3 would be a population 3 remnant. Basically, this is assuming that the black hole is going at the maximum rate it can. It's called the Eddington limit. And such a seed can grow at an Eddington limit to 10 to the power 9 solar mass if there is obscuration.
Yeah.
Thanks for the really interesting talk. I have a sort of very basic question about, I didn't really quite understand what this obscured growth is, and have these quasars with UV obscured growth been observed before, and if so, how many?
Right, there have been observed at low redshifts. I'm not sure about the number, but at high redshifts, we are yet to observe them. So obscuration basically means, I'm talking about UV obscuration, right? So the UV light from this quasar can be obstructed because of the presence of dust in front of the quasar, or just because we're not oriented in the right direction towards the quasar. But because of if there is dust, there will be emission from the dust in infrared, and that could be detected. And if so the black hole can still grow while it's being obscured. It's just that we are unable to see it. Is that clearer or?
Yes, thank you.
Last question.
Yeah. So it's a really nice talk. I wanted to ask about, so one comment is, I think in Cosmos and other surveys, we do have evidence for 70% of black holes being obscured, AGN being obscured at high redshift. So that's adding a lot of weight to your argument about them needing
Yes.
them.
Right, there was a reason. Yeah.
Yeah. Secondly, if you have, can you turn this argument around to get a patchy reionization constraint from the observed, proximity zones and your model? So for example, can you get a constraint on how it proceeded?
Yeah, so as you can see, this effect of patch reionization is pretty weak. It's not that big of an influence. So it seems to be more dependent on the evolution with lifetime is greater than the dependence on patch reionization. So
Sorry, I meant the red and the blue, the scenarios.
red and the blue.
Yeah.
Yeah, so red is actually an extreme case. At redshift 6, you wouldn't assume a completely neutral. But the other thing we've been looking at is getting a damping wing, for example. That's probably a better way to constrain neutral fraction than the proximity zone size. We could also compute the power spectrum within the proximity zone. That's also something that we're looking at. And that these probes would be better to measure the neutral fraction instead of a proximity zone.
Thanks, Sindhu. And let's thank all the speakers of this session.